In this video, I'm going to attempt to introduce the concept of frequency response analysis, determine its relevance, and explain its importance in chemical engineering controls. Frequency response analysis is primarily the idea that we can ascertain sort of a quantitative measure of how robust our system is to certain disturbances. For example, if I were to say, I have a control system by which I have an input and an output. Oops. Now, obviously we've seen graphs like this before. For example, this might be our U of t, and this might be our Y of t, our output. So I have my input at some initial steady state condition. But perhaps we make a change to the input, a step change. And so then our output, maybe it's initially at this value, our output changes as a function of that input. And how that changes is based obviously on its transfer function. Perhaps it looks something like that. Now, the idea of robustness in a controlled system is what sort of changes can I have in my input that will still allow my output to be maintained within a desirable range. So we've seen things like this. However, rarely is our system truly at any sort of steady state, right? As you may have seen if you've ever seen a true process control board, oftentimes the measurements that are coming in may look something like this. And maybe that's a bit exaggerated, but maybe they look something like this. And then you're going to have some sort of change, right? And then, so maybe your output is responding appropriately, and then it's going to change even more so as a function of time like that. So at what point does the magnitude of oscillations, the frequency of oscillations, or does the change that we input into the system truly affect our system's stability? That's the question that we're going to answer through this frequency stability analysis. Okay, I think that provides kind of a good starting point in terms of our motivation for attempting to ascertain kind of the complicated mathematical concepts that we're about to go over. So this is going to kind of really lean heavily on the ideas introduced in previous videos, specifically transfer functions. So I encourage you to watch my playlist number 4 for PDC, as well as process models, which would be more of homework 3, stability, homework 2, and of course, we're going to introduce some new concepts here in this number 5. Okay, so we're going to talk first about what it means to even begin to be able to tackle the idea of a sinusoidal input in terms of stability. So there is a common substitution that is made into transfer functions, and that is this substitution right here, S equals JW. What that substitution does is it yields us a long-term frequency response of our transfer function to a any sort of oscillatory, whether that's sine or cosine, sinusoidal type oscillation input. So first we're going to go over why that's the case, and then we're going to kind of define 2 terms as a result of this substitution. So let's dig in right here. Um, so basically, there are two primary methods that we could use to basically attempt to see what sort of change our input is going to give us. And the one that we should be already familiar with is converting that input into some sort of Laplace domain type function. Let me write it out, and it might make a little bit more sense. So, for example, we have this input u of t, and we're going to define it as some sort of arbitrary sinusoid with amplitude a and frequency omega. Now, obviously, we're going to need some sort of process function here. So I'm going to just use a simple first order process. However, this will work with any order process. There will just be additional cancellations that will take place this step that I'll show you soon. So I'm going to define our process function GP as some KP parameter over tau P S plus 1. Okay, so given this information, the first thing that we're going to do is convert our input into the Laplace domain. So using a Laplace table, or by actually performing the Laplace transform, what we should be able to show is that a sine omega t should be easily transferable into a omega over sine squared plus omega squared. Okay. Thus, the output y of s is going to be what? It's going to be our input multiplied by our process gain. So we should have AP over tau PS plus 1 times a omega over s squared plus omega squared, right? So the next thing that we're going to do is we're going to decompose this term into partial fractions. Partial fraction decomposition, or PFD, and then we're going to go ahead and invert it. So I'm going to go ahead and combine those two steps here, and we'll end up with, so invert meaning bring it out of the Laplace domain. And so after we perform that, what we should see is that y of t gives us kp a omega tau p over tau p squared omega squared plus 1 e to the negative t over tau p, right? Plus what? kpa over tau p squared omega squared plus 1 sine omega t. And there should also be a cosine term on here as well. That should look like this. Tau p squared omega squared plus 1. And then I should shrink this down a little bit. This would be cosine omega t. Right? Okay. So from here, we should be able to notice some things about the function. Primarily that we have a pretty clear trigonometric identity here, right? So, um, so here's going to be our trig identity, right? And we're going to end up with a sine, what would this be? Omega t plus phi, where phi is going to be our phase angle here. And then how would this work? We need a magnitude here, so this will be kPa over root tau p squared omega squared plus 1. So that should be that. Now, again, remember or recall rather that we're looking for a long-term frequency response here. And thus, as t approaches infinity and this exponential term here, this entire term will end up going to 0. So we have y of t as it approaches infinity. Of course, our phi here is going to be the inverse tangent of what? Of negative omega tau p, right? And we can also define a term called the amplitude ratio. And what that is going to be is magnitude of y over magnitude of u, which of course in this case will simply be kp over square root tau p squared omega squared plus 1, right? Okay, so that is our long-term, here's our long-term response. Via Laplace transform. Okay, and we've just gone ahead and defined 2 other terms that will come up very shortly here for us. Okay, so the next thing we're going to do is we're going to attempt to substitute the term S equals JW into our input term here, and then attempt to see how that influences our calculation. So A omega over S is going to be J omega, so J squared omega squared plus omega squared times our process function here. And we're going to go ahead and input J omega in down here. Okay. So what we're going to work with next is we're going to go ahead and multiply this across, I believe. Let's see what this gives us. AK omega over it's going to be tau p j cubed omega cubed plus j squared omega squared plus tau p j omega cubed plus omega squared, right? Now, what can we do with this here? Actually, wait. I think we should just be substituting into our process function here. So GPS equals Kp over tau p j omega plus 1. And then multiply both terms by tau p j omega plus 1. over tau p j omega plus 1 will give us what? No, it does nothing. We need to be multiplying by the conjugate here, right? There we go. Okay. So that'll give us negative kp tau p j omega plus kp over what? Negative tau p squared j squared omega squared plus 1, which ends up equaling what? That should be kp over tau p squared omega squared plus 1. And again, this is just simply separating the fractions here. So that should be negative, and then minus. Actually, wait, should that be negative or positive? It should be positive. But this will be negative, minus kp tau p j omega over tau p squared omega squared plus 1. And this can have a j out front. So thus, we've successfully created a real and an imaginary portion of our process transfer function. So of course the magnitude here is going to be simply square root of real squared plus imaginary squared, which in this case will give us what? Square root of kp squared. Let's go ahead and do this here. 1 plus tau p squared omega squared over 1 plus tau p omega. Both of these should probably be squared, that quantity squared. If we go ahead and simplify that, what do we get? That should be kp over square root 1 plus tau p squared omega squared, which is the amplitude ratio, right? It's exactly the same as this quantity here. Similarly, our phase angle, we called phi, is going to be inverse tangent of what? It should be our imaginary component times our real component. Negative, should be our let's try this. Tan negative 1 of what exactly? Our imaginary component here. Times 1 over our real component, which would be simply tau p squared omega squared plus 1 over kp. After cancellations, oops, the one thing that I didn't need to cancel here. We're left with inverse tan negative tau p omega, which of course is exactly the same relation that we've constructed right here. Okay, there we go. That kind of describes in its entirety why the S over J omega value works here. Again, we're going to be constructing a real and an imaginary component, and then constructing our amplitude ratio and our phase angle I in both of those cases. So, pretty long math derivation. However, the significance of this truly lies in sort of making physical significance out of these two values, this amplitude ratio and this phi here. And we'll go a little bit deeper into that, into what exactly each of these ratios mean in the next video, where we're going to actually plot these and then simulate how the system is responding to these different plots. However, I think kind of a general explanation of what these two values really mean is kind of incumbent right now. So let's talk about it. Basically, these two ratios are two different things. So first of all, our amplitude ratio is going to basically plot on the same scale our output and our input against time. Now what's happening here, this white curve will be my input. Actually, I probably need to stretch this out a little bit to make it a little bit more visible. Okay, so this is my U. And then I'm going to have a another term here. Let's call this Y. And I'm attempting to do this, but I'm not going to really do it. Let's just do, yeah. We're going to pretend that those oscillations are perfect. So this will be my Y. And so basically what we're going to define here, number one, is this line right here, right? The amplitude of our sine wave, we remember back to algebra 1, or algebra 2, maybe, is just simply the ratio of these two lines. So let's actually make this line red and this line white. So we'll call this, we'll call that length a U and this length a Y. And so what the amplitude ratio is simply a comparison of these two magnitudes. So it's amplitude of the output over amplitude of the input. Similarly, we're going to define another value here. So we're going to look at the peak to peak here and call that delta P. And between the waves. And then we're going to call peak to peak on the input wave regular P. And what our phase angle is simply the change in peak over peak. And this is the phase shift of the output to the input here. This obviously times negative 2 pi to represent one complete oscillation. And so kind of this definition of the phase angle brings into context the importance of the Baudet plot, simply because let's see what happens if we plug in negative pi radians into this formula here. So we say that phi is equal to negative 2 pi times delta p over p. Now, a really interesting kind of characteristic is what happens when we look at negative pi here, right? Okay, and so let's go ahead and solve here. So dividing across, we'll have delta p over p is going to be what? Pi. So one, or a complete offset, complete phase shift out of each other, right? And so what does this really mean? Well, what this means is, if we were to look back at our control block diagram here, here's R, and here's E, here's U. Basically what this means is that our output is constantly out of shift with our input, or our set point here. So, for example, in this case, basically what we have happening is the magnitude, sorry, not the magnitude, but the trajectory of this wave, this amplitude of oscillation of our set point here. Let's draw this of our set point. Is perfectly out of phase with our output. And now you may say, well, what's wrong with that? It makes it really pretty double helix. Well, what's going to happen then, in this case, is that, well, the negative sign on this angle, or rather the positive sign incurred as a result of dividing by the negative, means that every time we attempt to look at a set point, right? So let's say I want to look at, right here is my input signal. Well, my output signal, which I'm going to add to it, is going to be negative. Well, that would be fine if on the control block diagram we had a positive right here, but we don't give it positive negative, which means that really what's happening is that as this signal comes in completely opposite of this signal, I'm taking a positive of some magnitude A and subtracting a negative with some magnitude A, which means I have a continued growth of that output. Well, if the phase angle stays the same, well, what's going to happen? Well, this is going to get even more negative and then even more positive, and as a result, this will get even more negative and even more positive and then positive and then negative and begin to expand. And what you have is you have an unstable system. So what this means is that as soon as you hit this value in your phase angle calculations, what you found is that your system is no longer stable and is going to be fluctuating. Its oscillations will continue to grow, leading to instability. So hopefully that kind of clears up this kind of magnitude ratio phase angle relationship a little bit. I think it becomes really clear once we simulate it with more than poorly scribbled lines on an iPad. And that's what we'll do in my next video. See you then.